Hello, ladies and gentlemen. My name is Jeroen Reiniers of Separation Science, and I would like to welcome you all to our latest webinar in collaboration with Agilent. Our topic today is connecting performance improvement to increase production in GCMS analytical workflows. Let me introduce our presenters for today's webinar. Angie Smith-Henry is an applications chemist for GC and MS supplies at Agilent in Wilmington, Delaware, USA. Previously, she was an applications chemist for the MSD Solutions and Applications Group with a focus on developing analyzers and applications for energy, chemical and environmental markets. Angie holds a PhD in physical chemistry from Lehigh University and a Bachelor of Science in Chemistry from Juniata College. Gustavo Serrano is the GC Columns Product Manager at Agilent in Wilmington, Delaware, USA. Gustavo has a broad background in GC technologies, including experience as an R&D scientist and product manager at Sigma Aldrich Supelco, where he worked on development and commercialization of novel GC stationary phases. He has also published extensively in the fields of portable micro GC systems, GC columns and microthermal modulators for GC-GC applications. Gustavo holds a PhD in Environmental Health Sciences from the University of Michigan and an MBA from the University of Indiana, Bloomington. And so, without further ado, I'll turn the presentation firstly over to Angie. Angie?
Thank you. Gustavo and I welcome you all to our talk about improving performance and increasing production in your workflows. Many questions can formulate in your mind when working with GCMS systems and analyses. How can I minimize downtime and maximize lifetime and sensitivity with the best supplies? Could ultra inert deactivated products help my analysis? Is there any way to minimize the number of times I have to vent and trim the column? Am I using the right tune and temperatures for the mass spectrometer, or do I need to run the mass spec at higher temperatures? Today we'll discuss a number of these ideas, from selecting the right liner and column for your application, to the various techniques that can be used with Capillary Flow Technology, or CFT, and how to make those CFT connections. And then we'll wrap up with a discussion on the optimal conditions on a single quad and tandem quad mass spec. To summarize the previous slide, let's discuss what to use in splitless and split injections. So if you're running trace analyses of sensitive compounds in a dirty matrix like food, a splitless injection and liner would be best, with a single bottom taper and either glass wool or glass frit to provide filtration and a site for volatilization. Plus, ultra inert deactivation enables excellent peak shapes for tricky analytes. If you're running an analysis with higher concentration compounds that are not as reactive, then a split injection is what you should probably use. Be sure to use a split or universal liner to allow for space for the split flow, with wool in the upper to middle section of the liner. And you could either use a straight or tapered liner for these analyses. An example of each style is shown on the bottom right side of the slide: a split straight liner with glass wool, and also a universal tapered liner with glass wool, both with ultra inert deactivation. Now remember, do not do split injections on a splitless liner. There's not enough room for the split flow, and the analysis will suffer from poor reproducibility. So one downside of glass wool is that fibers can become dislodged and get into the head of the column, or the glass wool can break and expose new active sites, which can cause a number of issues, including response loss and compound degradation. A way to step around the wool issues is with using a fritted liner. So you may have some questions about how the fritted liners stack up against wool liners, and we'll discuss that on the next few slides. First example is showing an EPA 8270 style analysis between the splitless glass frit and glass wool liners, where semi-volatile organic compounds were analyzed in soil matrices. We wanted to verify that the responses were similar to wool liners on the fritted liners so that you could easily switch from wool to fritted liner and not observe significant changes in the continuing calibration verification checks. The figures shown here and the inset show that the fritted liner and 3 different wool liners of the same style but different deactivations have matching responses. We then completed a lifetime study and observed that the starting DDT breakdowns were very similar across all 4 liner styles, but the glass frit liner lasted twice as long as the glass wool liners. So fritted liners have similar responses for semi-volatiles, but you get double the number of injections. Just think about how many more samples you could run in your system before having to cool down the system to reset and recalibrate in that situation. Furthermore, we did a similar style of analysis looking at pesticides in food, comparing splitless glass frit, glass wool, and carbon frit liners of similar styles. And we were looking at food matrices that included spinach, plum, orange, and onion. So here we have 2 sensitive compounds that are prone to degradation, endosulfan sulfate on the left and DDT on the right. The glass fritted liner had higher responses at 10 part per billion for these sensitive compounds compared to the similar style liners with glass wool or carbon frits. For some of the later eluting compounds in our analysis of pesticides in food, we also observe less peak tailing on the fritted liner than the glass wool liner for deltamethrin and azoxystrobin, and also we observe significantly higher responses for deltamethrin on the glass barrier liners, the glass frit and glass wool, compared to the carbon frit.
All right. Thank you, Angie, for that great introduction and talking about everything related to the GC inlet and liners. And it's time to talk about the GC column for GC-MS operations and the importance to choose the right columns to maximize your lab productivity. All right. We have talked in previous webinars about the importance of choosing the right GC column for your GCMS applications. We talk about how important is inertness and low bleed profiles. As important as those aspects is also the right column dimension. However, there was one topic I haven't discussed and that I want to discuss further in this webinar, and it's that inertness and bleed are important, but it's as important or even more important to keep that same inertness and low bleed profile for extended periods of time. So if you have good inertness for one injection or maybe 5 or 10, but then you start to lose inertness over time, then that's bad, right? And then it's time to change the column. It's downtime to go through troubleshooting and see what's going on. So it's critical to have good inertness and low bleed for long periods of time because that translates into more analysis before you have to change your column. And that's the topic I want to discuss for GC columns in this webinar. So going back to my previous slide, I think this one shows, what happens with your analysis after several injections, hopefully hundreds of them, right? Because a column is a consumable, it has a column a lifetime, and the purpose that I want to show you this webinar is just how to extend that as much as we can. But certainly the column has an expiration. It depends on your matrix and things like that. And I'm open to questions if you have for your specific cases. But just wanted you to visualize how does the chromatogram looks after a column is not performing as it should be. It's mostly 2 things that are easily to identify. The peak tailing, this is because of the creation of active sites. This is because silanols are now present, maybe due to oxygen. And the other is the retention time. And retention time changes because we're losing the stationary phase, right? The bleed is a stationary phase that is just being removed from the column and going into the detector. So these are the two conditions that we're trying to solve and see how we can optimize our column so that we don't get up to this point. So first things first, I think that if you have concerns about how to improve the efficiency in your lab, how to get the best results out of your GCMS, the starting point is the Ultra Inert GC column, and I hope I don't sound like a broken record, but it is certainly the best starting point for any analysis you may have to do. Ultra-inert columns is the last generation of GC columns. This is Agilent's proprietary technology for deactivation and eliminate active sites. Um, it shows improved peak shapes at low levels for acidic or compounds, for example, so that you get better sensitivity under same conditions compared to a non-ultra inert column. Um, so it's reliable, it's very inert overall, and you will have more consistent data over time, which is the aspect I want to emphasize in this webinar. The selectivity is a question that we generally have from some customers, and it's the same selectivity. So if you are using a DB5 MS, you will get the same selectivity out of a DB5 MS Ultra Inert, and the same with HP5 MS. This is I like to mention this because the column from the last few years, like this one, is not the same column as the one from 20, 25 years ago. It's this different technology, and you should benefit from the advantages in column development. So right now, with Agilent leading the market in GC columns, we have the best technology for GCMS analysis through this new development in ultra-inert columns. Here is an example of DB5MS Ultra Inert compared to a standard 5MS from a different brand. You can see already the improve on inertness from several of these compounds. Particularly, you can look at PIC6, the trimethyl phosphate. You can just see the improvements in the tailing factor. So ultra-inert columns, the DB5MS, HP5MS, or DB35MS ultra-inert are all consistent in this reproducibility and robustness for acidic or basic compounds. The DB5MS or HP5MS, they should be your to-go column for any GCMS applications. If you want additional polarity, for example, we see a lot of for MCPD analysis in oils or in food samples. We need a little bit more polarity, and I've seen customers using DB35MS UI. So certainly we're trying to cover all range of applications with ultra inertness. We also have the DB-Wax UI, and DB624 ultra inert, and we have one application specific, which is DB8270 ultra inert, specific for semi-volatile compounds. We will talk about applications in the next few slides, but just wanted to give you, if you're not familiar with ultra inertness, of what ultra inertness is capable of. So we're going to start with the initial thought that I gave you at the introduction of my part of this webinar. It's about being consistent and reliable, and it's about how far can I push my columns. Sometimes you see other vendors some pretty nice looking chromatograms, but then we hear from customers that yeah, but after 20 injections I have to start cutting the column a few centimeters. The tailing factor is too much, and I have to replace it. This is the 5MS UI. The bottom chromatogram is the initial chromatogram. This is a test mix with some challenging analyses. We have alcohols, acetones, ketones, aldehydes, acids. And you can see the behavior of the column after 60 hours at 350 Celsius. This is when you start to see in a poor, with a column with a poor performance, you start to see tailing and huge changes in selectivity and retention time. With the 5ms UI, you don't see that at all. You see maybe some changes in retention time, and that's because of the column bleed, but it's minimum, and you can certainly use retention time locking if you have to. But overall, look at those peak shapes, and if you are looking for trace levels, this is the type of consistent inertness that you're looking for in a GC column for extended productivity. Well, to move away from chromatograms, I just wanted to show you this plot on tailing factors for several 5ms GC columns after several heating cycles. Um, this is another way to translate what I was discussing in the previous slide. Tailing factor obviously will tell us a lot about the inertness of the GC column over long periods of time. In this case, up to 70 hours for our columns. But you can look at and compare the tailing factors for our columns and two different vendors of GC columns. And you can see how with DB5MS Ultra Inert, you get very consistent tailing factors over a long period of time. So why is this important to you? Why is this useful? Yeah, I mean, you're obviously you're not running this type of tailing factor as part of a fundamental study of your GC column behavior, but it just translates into a better column lifetime, into enhanced performance out of your column, and not just out of the box, but for several months and several injections and several analyses. And that's what productivity is all about, right? Because if you have this level of consistency over this long period of time, that means less downtime and less time to do troubleshooting. Um, a lot of, I've seen in other vendors probably that when they talk about column lifetime, they measure number of theoretical plates. I think that translated to performance, but generally theoretical plates are calculated with an alkane, right? Because the alkanes they don't tail, they don't have any active functional group. They are just alkanes. But doesn't really tell you the whole picture, right? If you want to see the whole picture about performance over extended period of time, you have to look at inertness as well, not just performance. So that's why we do a lot of tailing factor analysis at Agilent so that we can learn how our columns perform over time. So this slide may sound a little intriguing. It's how inert is your ultra inert GC column. It's very and very robust too. And thank you for asking. And I'm saying that because if you look at literature out there, one of the other GC column vendors, they did a performance on butanediol, comparing their columns with our 5ms UIs and HP5ms UI, and they didn't make we didn't look very good in those comparisons. And so it's something that we have to evaluate. Obviously, if there is an issue, we would like to resolve it and see where the problem was. But there wasn't any issue, and this is the analysis of butanediol. Again, no peak tailing out of the box. I would not even recommend butanediol as a measure of column performance or of inertness. I think an acid compound will be more challenging, but maybe their column wasn't really responding for acids. But out of the box, butanediol looks really good with DB5 MSUI, and over time, look at the symmetry values. It was almost perfect. It was around 1 over 50 hours at 350 Celsius. So, when you do competitor studies, it has to be in all fairness, and I think that's what we're trying to do here. We're not mentioning any other vendor, so we don't want this webinar to be that, but we do have to defend ourselves when this information comes into public information. But yes, and they had that question, right? How inert is your ultra inert? And I think the answer is very, right, and consistent, right? It's not just one chromatogram only. I think we discussed plenty about inertness and the importance and the benefits of keeping that inertness as a measure of column performance over long periods of time. Um, However, let's not forget about GC column bleed. This is as important. The lower bleed profile will allow you to analyze trace level analysis, especially for the heavier compounds, the high molecular weight. If your bleed is too high, then you will get a very small peak because the rest of the peak is probably buried in that bleedness coming from the column. So it's very important to keep that low profile, and that's what our 5MS UI columns, what they do. But also as important is to keep that low bleed profile consistent over long periods of time. So here again, this is another study in which we were trying to analyze and observe what happens during 50 hours in this case. And you can see that the baseline changes were minimal. That means that your bleed profile will help you to be robust in your data. What happens is that in some cases your bleed may go up, may go down, it may affect your retention time, and if your bleed goes up or down to match, then that increases your relative standard deviation error. And that means that even though you are able to quantify your analyte, your standard deviation will be all over the place. So it's important to have that consistency over time for inertness and also for bleed. To wrap up my part of the presentation, I will just show you a few applications and the study that we did over time for some of them for DB5MS Ultra Inert. A typical use for DB5MS or HP5MS Ultra Inert is the analysis of pesticide analysis. This was a matrix injection of acidic pesticides. This may not look like yours. I know that for some of the pesticides in food, you see hundreds of them. But this was a fundamental study on the acidic behavior of the column towards these very challenging compounds. So this was a very, even though the mixture is simple, the set of analysis is very challenging for any GC column. So you can see that most of these are chlorophenols, right? So you can see again the out-of-the-box GC column, and after 200 matrix injections, look how we can keep the consistency in retention time and inertness for this column. Again, very important for your day-to-day use of the column and extend column lifetime for this type of challenging analysis. Another application that is very popular with DB5MS Ultra Inert or HP5MS Ultra Inert is the analysis of semi-volatile compounds. We also have one called DB-UI 8270. This is specific for 8270. But nevertheless, here is also the study about the behavior of these compounds, who are very heavy, also very challenging, and how robust can the column be for this type of applications. So here is also a soil sample for semi-volatile analysis. This is a checkout mix with several challenging compounds like endrine, anthracene, another chrysene. I see a lot of semi-volatiles that are part of the EPA 8270. But again, this is a fundamental study just to look at what happens with a column out of the box and what happens after 200 injections of matrix injections. These are very difficult, and I think Angie is going to talk about backflush. This is another way to improve column lifetime out of your column because you're getting all these matrix away and not going through the analytical column. But again, good inertness, very good reparability of retention time, and that means that after 200 injections, you will get the same results, the same RSD levels, and the same reproducibility. That is very, very important, especially for trace level analysis. The last application I want to show is on analysis of PAHs. Again, very similar results. For PAHs, it's very, it depends on the method, on the sample you're using. The polarity of the column will change. This is the example for DB5-MSUI. Some of these PAHs are also part of EPA 8270. But if you're doing PAHs in food or you're using the European methods, then you need a different polarity. And for that, we have two columns, select PAH and DB EU PAH. These are just higher polarity columns that will allow you to separate triphenylene from chrysine or the benzo BJK. I don't want to go a lot into pH analysis, but again, just wanted to show you all the reproducibility studies that we did over a long period of time for this type of analysis, because these are not easy. These are not, simple volatile compounds. These are challenging for your compound and for your system. So you have to have the right liners, the right septa, and the right column so that you are more consistent in your analysis and spend less time in troubleshooting or in downtime. So with that, I want to thank you for your attention, and I think it's Angie's turn again. So back to you, Angie.
Gustavo has provided great information on boosting performance and increasing productivity with columns. So let's see how we can make those columns last longer and potentially even get more information out of the sample with capillary flow technology devices. Why might a user want to try capillary flow technology or CFT devices? In some cases, you may need to split between two detectors, such as two FIDs or between a mass spec and electron capture detector. You may need to get some unique separations out of the analysis. There could be a pair of compounds that coalute on a compound, but if you transfer that coelution onto another column, they can be separated. CFT also provides the potential for higher data quality, faster cycle times through backflush, which can lead to more uptime and less maintenance with higher sample throughput. Now there's several CFT devices. These include the Ultimate Union, the Purged Ultimate Union, multiple splitters, two-way, three-way, both purged and non-purged, and also the Dean switch. Let's focus on detector splitting first. So splitters are used to split signals between multiple detectors, whether the analysis requires splitting between 2 or even 3 detectors. For example, you may split a signal between a mass spec for your structural and unknown compound identification, an ECD to identify your chlorinated pesticides and confirm them, and also an FPD to look for a sulfur or phosphorus compound confirmation. For any splitting between a mass spec and another detector, a purge splitter must be used to help keep the balance of the split flows. Comparatively, splitting between 2 atmospheric detectors, such as 2 FIDs or an FID and an MPD, a simple unpurged splitter can be utilized since the outlets are balanced. Another application for CFT devices is backflush. Backflush can be used to rid the less or non-volatile matrix that migrates onto the column after the analytes of interest have eluted, which can help decrease your run times, increase throughput, and also can decrease the frequency of how often you have to do column trims. Backflush is applicable across many markets and can use different CFT devices such as splitters or the purged ultimate union. Shown here is an example with a 15 by 15 meter mid-column backflush setup. And this is commonly used in pesticide analysis, but it's also applicable to environmental semi-volatiles analysis with dirty matrices. Now the column 1 could be shorter than column 2, do like a 5 meter by 15, or column 1 could be a retention gap instead of a separating column. It depends on what you need to match and fit your analysis. So this example of backflush uses a purged ultimate union. Now of course the secondary pressure module is needed to supply carrier gas to the mass spec when you are running a system with a backflush or doing any type of CFT device work with a mass spec. Now benefit that comes up when you have a CFT device that is purged is that you can change or trim your guard column or first column without venting your mass spec. And since the mass spec ion source is heated, it requires carrier gas flow to prevent oxidation and damage to the source components that are under vacuum. So we can completely avoid breaking vacuum while we're doing our head of the column and inlet maintenance when we've got a purged ultimate union or even a CFT splitter. So this can save a huge amount of time. You don't have to wait for your system to reach vacuum and re-equilibrate before you can run. And it also means you don't have to cool down the transfer line or ion source prior to doing the maintenance. You can just take your time replacing the liner, cleaning the inlet, or whatever maintenance you need to do on that first column without feeling rushed to get the system under vacuum again. Another benefit of backflush can be shown in the analysis of some dirty matrices, for example, fish oil. So we've done 10 replicate injections of 10% fish oil and acetone on a GCMS system. And what you'll notice is a shift in retention times by approximately 5 seconds across these runs. And this retention time shift occurred after every single injection. So you can see our retention times are migrating as we continue to inject our dirty matrix. Next, we ran a similar sequence of 10 runs, but at this one we ran backflush at the end of each injection of the 10 replicate injections, and we observed no retention time shift. Using backflush cures the retention time shift problem and helps keep them inside of their retention time windows. And that's especially important if you're looking at MRM transitions for GC tandem quad mass spec. Now CFT connections are a little different than our typical inlet and detector connections. CFT devices use special CFT nuts and that require pre-swaging, and they also require flexible metal ferrules. So we've improved on these flexible metal ferrules by adding a gold coating to the ferrules. And we wanted to take a few minutes to discuss the benefit of the flexible metal ferrule design compared to the older standard metal ferrule design. So on the left side, you'll see the standard metal ferrules, and what you'll notice is it has a tight pinch point. You can see indicated by the blue arrow, and it only seals at the tip of the ferrule, which can lead to crushing the column and leaks. Also, there's a coating of silver material on those metal ferrules, which is not compatible with the polyimide coating of the capillary column, and will eventually eat away at the polyimide at elevated temperatures, which can cause the capillary columns to break in the CFT fitting. Comparatively, the flexible metal ferrules have a broader sealing surface like a lampshade, indicated with those red arrows, which spreads out the sealing pressure to avoid a tight pinch point. This larger sealing surface area allows for a better seal without crushing the column or causing leaks. Furthermore, when using the gold-coated flexible metal ferrules, gold is inert and has no interactions with polyimide, so there's no worry about the columns breaking in the CFT device due to loss of polyimide. Additionally, with the gold ferrules, if there are any micro scratches or striations in the CFT device from previous use with other metal ferrules, the gold is soft enough to flow into these scratches and provide a leak-free seal without requiring extra wrench turns and repeated leak checks. In testing, users would install the pre-swaged gold ferrules in column into the CFT device with the required wrench turn and then leak check the fittings. No leaks were detected and no additional wrench turns were required, so the users were able to be up and running again quickly. They didn't have to spend time checking and rechecking the fittings before or after thermal cycles. I've mentioned a few times about needing to pre-swage the CFT ferrules. It's a similar idea to how you pre-swage swage lock fittings outside the GC. It's just using some smaller ferrules and tubing, and slightly different. So here we'll show you what you need and how to pre-swage the flexible metal ferrules. So you'll need your fused silica column. In this case, it's a 0.25 millimeter diameter column. The corresponding gold ferrule for that column diameter, which we have here. A CFT nut, the pre-swaging tool, a ceramic column cutting tool, a magnifying glass, and a 1/4 inch wrench. First, place the CFT nut and gold ferrule on the end of the column, with the tip of the ferrule facing the end of the column. Here's where the touchless packaging is great because you can use the column to pick up the ferrule out of the well in the dial pack, and you have less worry about dropping the ferrule or trying to pick it up and losing it. Next, you'll trim the column and inspect the cut. The cut should be straight across and free of burrs or any cracks. Then insert the column, ferrule, and CFT nut into the swaging tool. Try to center the column in the middle of the tool as best you can. And be sure to keep pushing the column into the tool to make sure it doesn't slip out as you finger tighten the CFT nut into place. One way to make sure the column is in the right depth is to hold the tool upside down, so with the nylon nut facing down towards the floor, and you'll gain some assistance from gravity. Next, you'll use the 1/4 inch wrench to pre-swage the gold ferrule onto the column. Note that each ferrule has a different range of turn radius to get the proper seal of ferrule to column, and this is a function of a column diameter. So for example, the ferrules for the 0.25 millimeter ID column has a swage range of 50 to 100 degrees. So you turn the wrench on the CFT nut approximately 50 degrees and then gently tug on the column. If it moves, push the column all the way back in and tighten by another 10 to 15 degrees. And you'll repeat this process until you cannot move the column. Then you're going to tighten it another 10 degrees to ensure proper swage. And you can remove the assembly from the pre-swaging tool, and you'll have a pre-swaged gold ferrule ready to install into a CFT device. So now that we've set up our GC side of the GCMS to be operating at its best with the right columns, supplies, and CFT devices, now we need to check in on the mass spectrometer setup. So let's talk about the mass spec zone temperatures, and the first question may be, do the temperatures really matter? And simply put, yes, the mass spec temperatures matter. Depending on your sample, a source or quad that is set too low in temperature can cause compounds to stick to the lenses in the source and reduce your signal, or increase peak tailing, or both at the same time. So for the source, the default is 230 degrees Celsius, which is good for volatile organic compounds and some other applications that use headspace samplers. But if you're doing liquid injections, the recommended temperature range is between 250 and 280 degrees Celsius. Generally, this range is warm enough to avoid peak tailing and compounds sticking to the source parts, but it also isn't so high that compounds degrade from the temperature. The specific temperature you use may require some optimization between 250 and 280. So watch the peak tailing and increase the source by 10 to 20 degrees as you test the results. The question may come up, is there any case where you may need to go above 280 degrees Celsius? And the answer is yes, when running polyaromatic hydrocarbons, or PAHs. It's best to keep the source on the hotter end, around 300 to 320 degrees Celsius, since PAHs tend to be very sticky compounds and like to stick to the source lenses. Looking at the quadrupole, the temperature applied here is a little more flexible, and the default of 150 degrees Celsius is generally what we recommend to use. The source has more effect on the peak response in the quad, but again, if running PAH-focused analyses, turn up the quad temperature slightly to 100 or 200 degrees Celsius. So in summary, our recommendations for most analyses is a source temperature around 250 or 280 degrees Celsius and the quad at 150 degrees Celsius. But remember, if you change your temperatures, you must retune your mass spec and give the mass spec enough time to come up to that temperature and settle in before you tune. Another way to optimize the mass spec is selecting the right draw-out plate or extraction lens for your application. Depending on the type of source you have, you may need a different part. For stainless steel and inert sources, a draw-out plate is utilized just after the source chamber. For the extractor or inert plus sources, an extraction lens was designed to have voltage applied to draw ions out of the source and can lead to an increase in response with the use of Etune. Now there are inert draw-out lenses and extraction plates in all three potential diameters, 3, 6, and 9 millimeters. Each lens works better for certain analyses. For example, semi-volatiles, pHs, and a few other analyses do best with a 9 millimeter lens, while pesticides and food work best with a 3 millimeter lens or draw-out plate. Now there are draw-out plates for stainless steel sources and different ones for the inert sources. The inert draw-out plates are indicated with a small dimple in each lens, the 3, 6, and 9 millimeter, and that's pointed out with the red arrow on the 9 millimeter draw-out plate on this slide. Now if you have both stainless steel and inert sources in your lab, remember to keep the different style parts separate. Inert parts should not be mixed with stainless steel parts, since that could cause different results in your chromatograms than expected. Now that we've changed our temperatures and extraction lenses, we need to retune the system. But what tune is best for what you need? Some analyses require specific tunes such as BFB tune or S tune, which we're not going to discuss today. However, most analyses can get by with the manufacturer provided tune. For inert plus or extractor source, the ones with extraction lenses, you have a choice between using A tune and E tune. Now A tune is the default typical tune, which is good for a lot, if not most, analyses and applications. Comparatively, there's also E-tune. Now when running and using E-tune, a voltage is applied to the extraction lens, and when tuning the mass spec, the voltage on this lens is optimized for the best transmission of ions. Generally, E-tune will have a higher signal since more ions are being pulled out of the source and sent to the quad, and may result in higher sensitivity and signal-to-noise ratio, but it's not guaranteed. If you're running scan on a single quad mass spec and E-tune, mass spec cannot select what fragments apply to the target analytes versus the matrix. If you have a dirty, heavy matrix, that background signal will also be increased at the same amount as the target analyte fragments, so you get no benefit necessarily from E-tune. However, if you're using a clean matrix or selected ion monitoring on a single quad, you may benefit from using E-tune. Could get a higher signal but retain a low background. And then with a tandem quadrupole system running multiple reaction monitoring, MRM, running E-tune can be a great idea since MRM acquisition can filter out much of the dirty matrix, and you still benefit from the greater potential sensitivity and signal-to-noise ratio of E-tune. Now we also have the high-efficiency source on this slide, and that also has a choice between A-tune and E-tune. The high-efficiency source, also called the HES, has a different design of lenses than the other sources and is really meant for trace analyses. The HES, when used in single quad applications with clean matrices, or when using selected ion monitoring, or SIM, in most of your analyses, can really get down to low detection limits. And for tandem quad systems, the HES really shines in trace level detection of analytes, such as dioxins analysis or very low levels of pesticides. Since we've discussed optimizing tunes, temperatures, and lenses, let's take a few minutes to focus on the collision cell of the tandem quad mass spectrometer. The collision cell is necessary to make reaction monitoring work and remove much, if not all, of the matrix interferences. To further break down the fragments coming from the source, we need to supply some energy, a collision gas like nitrogen, and also a quench gas then to stop those reactions and reduce background noise in the collision cell. So how do we know what collision energy we should set? A number of factors exist that affect collision energies: the carrier gas, the compound class, the specific compound, and even the specific transition of a compound. First off, let's focus on compound class. Depending on what compounds you are analyzing, different ranges of collision energies are applicable. Collision energy is the energy applied to further break apart the compound fragments. Some compounds break apart into their fragments easily and need a collision energy of 10 to 30 eV, but others don't, and may even need a collision energy up to 60 electron volts. For example, volatile organic compounds don't require as much collision energy, with most of the energies in the range of 10 to 15 electron volts. And nitrosamines also take a lighter touch, with electron volts between 1 and 25, typically. Pesticides range in the 10 to 25 eV range, while PAHs and dioxins are more difficult to fragment and generally take between 25 and 60 electron volts. And where do our semi-volatile compounds fall? Well, that can have a really wide range from 1 to 60 electron volts if you're looking at an analysis that includes everything from N-nitrosodimethylamine up to benzo-A-pyrene. The next question might be, if the compounds are in the same compound class, can they all be fragmented with the same collision energy? And so let's look at the table on the right for some examples from volatile organic compounds to PAHs. And you can quickly see the answer is no. Each compound has different collision energies, even inside the same compound class. For nitrosamines and N-nitrosodimethylamine, its transition of 77 to 44 mass to charge ratio was optimized at 6 electron volts, while the transition for N-nitrosopiperidine, molecular ion of 114 down to 55 mass to charge ratio, takes 25 electron volts. And we observe a similar pattern in the VOCs and pesticides and PAHs. Depending on the compound and its transition, the collision energies are different, but generally within a similar range. There are also more than just one transition per compound typically. Most compounds, we look at a quantifier and a couple qualifier transitions, and each of these transitions require a different collision energy sometimes. So focusing on a single compound from each compound class, we can see that phenol has the same collision energy for 2 of its transitions, while N-nitrosodimethylamine requires more electron volts for the transition of 74 to 42 mass to charge ratio of 22 electron volts compared to the transition 74 to 44 mass to charge ratio only requires that 6 electron volts we mentioned before. You may ask, does the collision energy depend on the size of the transition? Does a shorter transition take less energy? And the answer is not necessarily, and we can see that in the pH example. Here it takes 42 electron volts for the transition of 276 to 274, but only 30 eV to fragment from 138 to 124 mass to charge ratio. So the collision energy required depends on how easy the bonds are to break for that specific transition. So carrier gas also plays a part in collision energy. We know that helium and hydrogen have different viscosities and interaction with stationary phases and compounds, but it also has different effects on collision energies. So let's take a look at the effect that hydrogen carrier gas has on the collision energies of a couple pHs, fluoranthene and indeno 1,2,3-CD-pyrene. So looking at the same transitions for fluoranthene, less energy is required for both of the transitions when we have hydrogen as the carrier gas. The transitions go from 50 eV in both cases to 40 eV for that 202 to 200 transition, and down to 25 eV for the 202 to 201 transition. Now, does that mean hydrogen lowers all collision energies for all pHs? No. Remember, each transition will optimize to different energies. So the transition of 276 to 274 for indeno 1,2,3-CD-pyrene remains at 42 eV, while the 138 to 124 transition required a higher collision energy in the hydrogen carrier gas of 42 compared to 30 eV in helium. So are these differences in collision energy a problem or something to be concerned about? No. It's just a reminder that to get your best MRM acquisition results, you need to optimize the collision energies when you introduce new compounds to analysis or change something in the analysis, either in the mass spec or to your carrier gas. To pull our discussion together today, we've tried to provide some insight into optimizing your application. Using the right liners and columns for your application and setting up the mass spectrometer to get the most out of each run can lead to better data, sensitivity, and improved performance. Connecting further into the improved performance, Capillary Flow Technology can help take the analysis and productivity to the next level with backflush, splitting, or heart cutting, and the connections are easy to make that are leak-free with gold ferrules. Longer column lifetime from using ultra inert supplies and columns can be further enhanced with backflush to remove matrix from the column after every run. And using the ideal temperatures for your source and quad can help with better peak shape and less peak tailing. And finally, using the right extraction lens to match your application can help in reaching lower calibration levels with average response factors instead of linear fits.